Let's start by saying that we have some physical process, okay, and we know some variables involved in that physical process, and we are trying to find out a relation between those variables, okay, without really solving anything about the system. Let's say that A is a function of A1, A2, etc. ak plus 1, etc. an, where so a, I are all the independent variables in the system, and a is the dependent variable. So this is analogous to, if you think about the fluid flow past the object, that has been the problem that we have considered. So for example, the small a is basically the force is a function of all other variables like length, velocity, viscosity and so on. Okay, so the everything that you see on the right hand side are all your independent variables, and they decide some dependent variable in the problem. And let's say this function represents some physical process. That's where we have started with. Is that clear? Okay. Now, one thing that we could check is that, let's say that f actually has a multiplicative form. Now, once you do the proof, you will find that this has nothing to do with, this assumption is not really important. This is just to determine some number. What do I mean by that? I'm saying that, let's say a be given by a1 to the power of x1, a2 to the power of x2 and so on, ak to the power of xk, ak plus 1 to the power of xk plus 1, etc. an to the power of xn. Okay, so each of them are raised to some powers and then multiplied, and let's say that if that is the functional form, okay, this particular dependent variable has on the independent variable. And if I write down the dimensions, again I'll only worry about mass, length and time. So let's say, so the dimensions on the left hand side should match with the dimensions on the right hand side. Okay, so let's say the dimensions on the right hand side is L to the power of alpha, m to the power of beta, t to the power of gamma is equal to a1, let's say L to the power of alpha 1, m to the power of beta 1, t to the power of gamma 1 raised to the power x1 times L to the power of alpha 2, m to the power beta 2, t to the power gamma 2 raised to x2 and so on, L to the power of alpha k, m to the power beta k, t to the power gamma k raised to xk and so on, L to the power of alpha n, m to the power of beta n, t to the power of gamma n raised to xn. What have I done? I have just written down the dimensions for each of those variables. Of course, I do not know what those dimensions are. For a, I said it basically is some length to the power of something, mass to the power of something, time to the power of something. For a1, I said it's L to the power of some other power, okay, L to the power of alpha 1, m to the power of beta 1, t to the power of gamma 1, and the whole thing is raised by x1 and so on for each of the independent variables. That's okay. And the thing that I'm going to do is I'm just going to equate the powers for each of the dimensions. If I equate for alpha, I'll find, for length, I'll find that alpha is equal to alpha 1 x1 plus alpha 2 x2 and so on, alpha k xk, alpha n xn. If I equate the powers of mass, I'm going to get beta equal to beta 1 x1 plus beta 2 x2 plus etc. beta k xk, xn, gamma is equal to gamma 1 x1 plus gamma 2 x2 plus etc. Right? Just three equations, okay, where we do not know what are x1, x2 and so on, okay. So, if you look at it, what is this? So, we have n variables which are x1, x2 and so on, and we have got three equations, right? So, that means I can select n minus 3 variables independently and then that will fix the rest of the 3 variables, right? I have got linear equations, right, which has got n variables in it, but I have got only 3 equations, so that means I can select n minus 3 variables and the rest of them basically get fixed, correct? So that means I would be able to select n minus 3 variables. Okay, this is because I selected 3 fundamental dimensions, or if you generalize by saying that if you have k fundamental dimensions, then you can select n minus k variables which will fix, let's say, k other variables. This is what you would have done if you were solving the simple system of linear equations. Let's say, let x1, x2, etc. up to xk are the variables that are fixed. So let me just try to tell again, what are we trying to do? We have got a dependent variable a which is a function of lots of independent variables. By writing down the dimensions, I have found that if I can't have any arbitrary number of powers that I can assign to any of the variables, okay, if I talk about 3 fundamental dimensions, then I am allowed to take only n minus 3 I can independently choose n minus 3 variables, and that means I will be fixing 3 of them, right? 3 of them will be uniquely determined. So in general case, if I have k dimensions, okay, I am going to be basically fixing k quantities as fixed variables and n minus k will be independently chosen. Okay, so in other words, what I am going to do is that I am going to say that the first k variables are the ones that are going to be fixed and the n minus k variables are the ones which can be independently chosen. Okay, so and if you choose that the first k variables, so x1, x2, etc. up to xk are the powers of the first k variables. Remember, our functional form is a equal to f of a1, a2, etc. up to an. Okay, I am still going to be fixing these, and these from k plus 1 onwards I am going to be independently choosing. So are the variables that are fixed which belong to a1, a2, etc. up to ak. Okay, so a1, a2, etc. up to ak are the ones which I am going to fix and let x1, x2, xk be their powers which we have already taken, and let a1, a2, etc. up to ak are their dimensions. or simply what I'm saying is that A1 is nothing but A1, AK is same as AK. Okay, so for the first k variables, let's say capital A1, capital A2 and so on are their dimensions. Okay, and AK to AN or AK plus 1 to AN are the independent variables that I have, and I'm going to now represent the dimensions of these independent variables in terms of dimensions of the fixed variables. What am I trying to do? I am expressing dimensions of independent variables AK plus 1 etc. up to AN in terms of fixed variables A1 etc. up to AK. So the first kth variables, okay, you have fixed their dimensions. So let's take the problem of force is given by, let's say, mu rho L V. Okay, so there are, or I'll rewrite it in a different way. L V rho mu. What I'm saying, I'll say L V and rho I'm going to select as the fundamental dimensions so that I can represent the dimensions of mu in terms of L, V and rho, and I'll be able to do that, right? So similarly, I'm saying that if I have, n variables, I'll skip the first k variables, I'll select those dimensions of the first k variable, and then the n minus kth variables can be represented in terms of first k variables. This is the way you can represent a viscosity in terms of dimensions of L, V and rho. So that means if I have AK plus 1, dimensions of AK plus 1 can be written in terms of dimensions of the first k variable. Let's say A1 is the dimension of small a1, which will be raised to some arbitrary power, let's say P1, A2 to the power P2 and so on, AK to the power Pk. So I have the A1, this capital A1, capital A2, etc. up to capital AK are the dimensions of the first k variables, okay, and you are representing the k plus 1th variable, its dimension as a power of other variables, other k variables that you have already chosen, and so on. You could do it all the way up to, let's say, an, it should be another some a1 to the power of r1, a2 to the power of r2, so on, ak to the power rk. Similarly, you will also be able to write your dependent variable again. So let's say f, you want to write f in terms of L, V and rho. So small a, which is the dimension of the dependent variable, again in terms of other dimensions, let's say a1 to the power m1, a2 to the power m2 and so on, ak to the power mk. I'll take a pause and ask the questions if you have. Should I go through the procedure once again, or you're clear, or you're lost? Either say yes or no. Should I go through it again? So we are trying to prove Buckingham pi theorem, okay, and we want to do it in a general form. We don't want to take five independent variables, 3 dependent variables and so on. So I have taken a general function a, okay, with that. So I have taken, okay, a general function a, which is a function of a1, a2, etc. up to an. So that's the form that I have considered. Okay, now the first thing that I want to do is to find out how many dependent and how many independent variables that I can select. Okay, to do that, I'm going to say that let's say that this function is actually of a multiplicative form. That is, I'm saying that if small a, the dependent variable, is expressed as a power, as a multiples of powers of each of the variables. So a1 to the power x1, a2 to the power of x2, and so on. And if I do that, and if I write down the dimensions of all the variables, let's say the dimension of small a is in terms of L, M and T raised to some arbitrary powers, a1 raised to the power, so again, you know, each of them in terms of L, M and T raised to some arbitrary powers to the power of x1, because I have assumed that it's the power of, it's the function itself is a1 to the power of x1. So I have just written each of them as, you know, some L, M, T to the power of something. And if I equate the dimensions of each of them, then I basically end up with 3 linear equations. Of course, we did not know what x1, x2, etc. up to xn were, and that's our objective. We want to find out x1, x2 and so on. Okay, and we can't do that because we basically have 3 equations and we will have n unknowns, and we are ending up with n unknowns because we had n variables to start with, right? So we have n variables, 3 equations. That means that we have to select n minus 3 variables independently, and that will fix 3 variables as unique solutions, right? Because these are linear equations. You will be able to solve them and you will be able to find 3 of them. So that means in this problem, if I take this, as the form, I have to say that what is xk plus 1, xk plus 2, etc. up to xn. If I independently fix them, then I will be able to tell what is x1, x2, etc. up to xk, right? If I fix xk plus, if I choose xk plus 1, xk plus 2, etc. up to xn, then I will be able to tell what is x1, x2, etc. up to xk. Right? If I have 5 variables and if I have 3 dimensions, 2 of them I will independently select, which will fix the, you know, the powers of the other 3. Okay. So that's what that means we can select some of them independently and some of them as a fixed value. Okay. Now the idea is that we are going to represent all the fixed variables. Okay. All the variables that we are going to select as the fixed ones, which means this particular set, in terms of the independent ones that we are going to represent in terms of the fixed ones. So the dimensions of k plus 1 we are going to write in dimensions of a1, a2 and so on. So that's what I was telling you, this example, that if you have force as a function of L, V, rho and mu, so this is 1, this is 2, etc. and let's say this is the k plus 1th variable. The k plus 1th variable I will represent in terms of first k variables, or to be precise, the dimensions of k plus 1th variable will be represented in terms of k other dimensions of other k variables. So because I can represent the dimension of mu in terms of dimensions of L, V and rho, I can keep on doing that. I can add any other variable to this system and I will be able to represent the dimension of the variable that I am adding in terms of dimensions of the first 3 variable I have chosen, right? So in this system I have taken a k fundamental dimensions. So all the variables that I am going to have from k plus 1 onwards will be represented in terms of dimensions of first k variables. Okay, so this is the dimension of the k plus 1th variable. I have represented it as dimensions of all the first kth variables, and the dependent variable a, I can again represent it as in terms of dimensions of the first kth variables. Okay, if that's the case, then so what is our form right now? A is f of a1, a2, etc. up to ak plus 1, etc. up to an. This is the functional form that we had chosen. Okay, and we have said that we are going to represent the dimensions of all these Okay, the dimensions of these in terms of first k variables. That's all I have said so far. Now, let's say we select a unit system as A1, A2, etc. up to AK. So we might deal with unit systems like SIU, we will deal with unit systems like MKS. Instead of that, let's say we select a unit system which is given by the first k variables itself. Okay, if I do that, then that means each of the variable that I have can be expressed in terms of A1, A2 and so on. Okay, so if I do this, then I can write, let's say A represented in terms of A1, A2 and so on is A1 to the power M1, A2 to the power of M2, etc. up to AK to the power of MK. So that's a dependent variable. Is what have I done now? A is written in terms of the k variables that I have chosen. So if you like to think about, okay, let's say you have a system in which let's say you have you're dealing with acceleration. Okay, let's say acceleration is given as 980 meter per second square. So if you have chosen an SI system of units and you say that your acceleration is 980 meter per second square. But if you choose a unit system in which g is a fundamental quantity, then what would be acceleration? If g is the fundamental dimension that you have chosen, okay, then the acceleration would be just 100, right? Because it's 100g. Okay, so if you are choosing SI as the coordinate system, then you would have said, okay, 980 meter per second square is your acceleration. But if you select g, as a fundamental quantity in your unit system, then you will say, oh, my acceleration is 100. That will tell you what the acceleration is, right? Okay, so similarly, if you select A1, A2, etc. up to AK as the fundamental variables or fundamental quantities in your unit system, then A has to be divided by each of those variables to get the number that you are looking for. Just the way if A is equal to 980 meter per second square, if you select G as a fundamental quantity, then your A is nothing but 100. Okay, because 100g is going to be your your acceleration, some number. Similarly, if I have any variable, I can just divide it with whatever independent variables that I have chosen, raised to powers appropriately, and then I will get the so this is like the small a measured in a unit system which is spanned by A1, A2, etc. up to AK. No? I have selected a unit system in which my fundamental quantities are A1, A2, etc. up to AK. In this problem, f, which is a function of L, V, rho, mu, okay, I want to represent force in terms of a length, velocity and density. And then I would write F, okay, if I want to measure F, let's say it's some 10 Newton. I want to measure 10 Newton, but not as Newton, but in terms of things that are contributed by length, velocity and density. Okay, then I would have written it is L to the power of alpha, V to the power of beta, rho to the power of gamma. Of course, alpha, beta, gamma are to be chosen in such a way that it will basically will have the dimensions of force. So that's all what I am doing here. I am saying that I am selecting A1, A2, etc. up to AK as my units. so that I can measure any variable in terms of other k variables that I have chosen. So that means that's going to be equal to, I'll just write down the expression, we'll talk about it again. So A1 measured in terms of A1 will be just 1, A2 measured in terms of A2 will be just 1, and so on. AK plus 1 measured in terms of A1, A2 etc. up to AK will be again some A1 to the power of P1, which we do not know, A2 to the power of P2 etc. AK to the power of PK, and so on, all the way up to variables AN, which will be measured is A1 to the power of M1, A2 to the power of M2, some arbitrary powers, okay, AK to the power of MK. That's what we basically would get if we were, taking a unit system spanned by the first k variables. We'll stop there. We'll talk about it once again tomorrow. That's all actually Buckingham Pi theorem. It already says that what is that we need to do.